Okay, for today, we are going
تمام
to,
دكتورة.
right. So we are going to touch about the next chapter, okay, telephone and cable network for data transmission. Okay, on this chapter, I will explain about the circuit switching technology and then the packet switching networks, and then explain the concept of multiplexing, justify the usage of transmission media based on network requirements. So in this case, at the last chapter, you should be able to identify or justify, okay, why for certain type of transmission media, we are going to use that based on the network requirement. Okay. So there are two fundamental approaches toward building a network core. One is the circuit switching and then packet switching. Okay. Then in circuit switch networks, the resources needed along a path, or what we call as a buffers and link bandwidth, to provide for communication between the end systems, uh, which are reserved for the duration of the sessions. Okay, so means it's like a telephone network. Okay, when you try to call and then the call can pass through to the other end, so that kind of communication is what we call as the session. Okay, so they provide the buffer, they provide the link bandwidth, okay, for each end to be able to communicate. So in packet switch networks, these resources are not reserved. A session messages use the resource on demand, and as a consequence, we have to wait. That is like they are queuing, okay, for access to a communication link. Traditional telephone networks are example of circuit switch networks. Consider what happens when someone wants to send information using a voice or fax to another over a telephone network. So before the sender can send the information, the network must establish a connection between the sender and the receiver. So this is a bona fide connections for which the switches on the path between the sender or receiver would maintain that connection state for that connections. So in the jargon of telephony, so we call these connections as a circuit. Okay, in the old style, okay, so the operator need to switch on, okay, to connect to that circuit. Okay, and then once the call has been ended, then they will switch off that circuit. So when the network establishes that circuit, it also reserves a constant transmission rate in the network's links, representing a fraction of each transmission capacity for the duration of the connections. Like how many kilobytes was provided for that link. Since a given transmission rate has been reserved for the sender to receiver connection, the sender can transfer the data to the receiver at the guaranteed constant rate. So this is what it looks like of a circuit switch network. Okay, so in this network, the four circuit switches, okay, this is, we consider this as a circuit switch, are interconnected by four links. Okay, so each of these circuit switch, okay, they have an individual four links that connect to each other. So each of these links has four circuits, okay, four circuits each, so that each link can support four simultaneous connections. So the host, for example, like PC and workstations, are each directly connected to each of the switches. So when there are two hosts wants to communicate, the network will establish a dedicated end-to-end. So from one end to another end. Okay, that is like a dedicated connection between these two hosts. So the connection gets 1/4 of the link's total transmission capacity for the duration of the connection. For example, if each link has a transmission rate of 1 megabit per second, then each end-to-end circuit switch connection gets 250 kilobits per second of dedicated transmission rate. It's because of this one link contain four circuits, and then because they can support four simultaneously, so the capacity provided is divided into four circuits. Okay. Mm, if the message is going through to pass a packet switch network, it needs to be divided into packets of fixed or variable size. Okay. So the size of the packet is determined by the network and the governing protocol. So in a packet switching, there is no resource allocation, okay, for a packet, as the packets are transmitted over each communication link at a rate equal to the full transmission rate of the link. So most packet switches use store and forward, okay, transmission at the inputs of the link. Okay, store and forward transmission means that the switch must receive the entire packet before it can begin to transmit the first bit of the packet onto the outbound link. The store and forward packet switches introduce a store and forward delay at the inputs to each link along the packet's route. So within each router, there are multiple buffers, or what we call as a queues, with each link having an input buffer to store this packet that have just arrived to that link, and an output buffer. So the output buffer will play a key role in packet switching. So if an arriving packet needs to be transmitted across a link but finds the link busy with the transmission of another packet, okay, they must wait in the output buffer. So an arriving packet may find that the buffer is completely filled with other packets waiting for transmission. So in that case, packet loss will occur because either the arriving packet or one of the one that already queued packet will be dropped. In analogy, using a restaurant, the queuing delay is analogous to the amount of time one spends waiting for a table, and packet loss is analogous to being told by the waiter that you must leave the premises because there are already too many other people waiting at the bar for a table. Having described circuit switching and packet switching, okay, let us compare in between these packet switches versus circuit switches. Circuit switching. So packet switching have often argued that packet switching is not suitable for real-time services. For example, telephone calls and video conference calls because of its variable and unpredictable delays. Proponents of packet switching argues that packet switching allows more users to use the network. It offers better sharing of bandwidth than circuit switching, and it is simpler, more efficient, and less costly to implement than circuit switching. So generally speaking, people who do not like to hassle with restaurant reservations prefer packet switching to circuit switching. Recall the access networks can be loosely divided into three categories. We have residential access networks that connect a home and system into the network, and an institutional access networks that connecting an end system in a business or educational institution into the network, and then mobile access networks that connect a mobile end system into the network. So these categories are not hard and fast. Some corporate end system may well use the access network technology that we ascribe to residential access networks, and vice versa. A residential access network connects a home and system, typically a PC, but perhaps a web TV or other residential system to an edge router. So probably the most common form of home access is by using a modem over a POTS or plain old telephone system dial-up line to an internet service provider. The home modem converts the digital output of the PC into analog format for transmission over the analog phone line. A modem in the ISP converts the analog signal back into digital form for input to the ISP router. Access network is um, simply a point-to-point dial-up link into an edge router using twisted pair phone line. Today's modem speeds allow dial-up access at rates up to 56 kilobits per second. However, due to the poor quality of twisted pair line between many homes and ISPs, many users get an effective rate significantly less than 56 kilobit per second. Whereas dial-up modems require conversions of the end system digital data into analog form for transmission, so-called narrowband ISDN technology or integrated services digital network, okay, allows for all digital transmission of data from a home end system over ISDN telephone lines to a phone company central office. Although ISDN was originally conceived as a way to carry digital data from one end of the phone system to another, it is also an important network access technology that provides higher speed access, for example, 128 kilobits per second from home into a data network such as the internet. ADSL is conceptually similar to the dial-up modems. It is a new modem technology running over existing twisted pair telephone lines, but it can transmit at rates of up to about 8 megabit per second from the ISP router to a home end system. One of the features of ADSL is that the service allows the user to make an ordinary telephone call using the POTS channel while simultaneously surfing the web. So the data rate in the reverse direction from the home end system to the central office router is less than 1 megabit per second. The terms A in this case is asymmetry. So the asymmetry in the access speeds gives rise to the term asymmetry in the ADSL. So the asymmetry in the data rates reflects the belief that a home user is more likely to be a consumer of information, like bringing the data into the home, compared to become a producer of information. ADSL, ISDN, and dial-up modems all use ordinary phone lines, but HFC or hybrid fiber coaxial access networks are extensions of the current cable network used for broadcasting cable television. As illustrated in the figure, fiber optics, this one, fiber optics connect the cable head, okay, into neighborhood level junctions, from which traditional coaxial cable is then used to reach individual houses and apartments. Each neighborhood junction typically supports 500 to 5,000 homes. Cable internet access requires cable modems, an external device, and connects to the home PC through an Ethernet port. At the cable head end, the cable modem termination system or CMTS serves a similar functions as the DSL network DSLAM, turning the analog signal sent from the cable modem in many downstream homes back into digital format. Cable modems divide the HFC network into two channels, a downstream and an upstream. Okay, so as with DSL, access is typically asymmetric, with the downstream channel typically allocated a higher transmission rate than the upstream channel. One important characteristic of cable internet access is that it is a shared broadcast medium. Every packet sent by the head end travels downstream on every link to each home, and every packet sent by a home travels on the upstream channel to the head end. If several users are simultaneously downloading a video file on the downstream channel, the actual rate at which each user receives its video file will be significantly lower than the aggregate cable downstream rate. On the other hand, if there are only a few active users and they are all web surfing, then each of these users may actually receive web pages at the full cable downstream rate, because the users will rarely request a web page at the same time. So because the upstream channel is also shared, a distributed multiple access protocol is needed to coordinate transmissions and avoid collisions. All right, an up and coming technology, this is the current one that provides an even higher speed, is what we call as a fiber to the home, where it provides an optical fiber path from the central office directly to the home. Okay. There are several competing technologies for optical distribution from the central office to the homes. The simplest optical distribution network is what we call as a direct fiber, where each fiber leaving the central office is actually shared by many homes. It is not until the fiber gets relatively close to the homes that it is split into individual customer specific fibers, as what you have experienced when you are trying to subscribe the Unify in Malaysia. And then there are two competing optical distribution network architectures that perform this splitting: active optical networks, or AONs, and passive optical networks, PON. The figure shows FTH, fiber to the home, using the PON, okay, passive optical networks architecture, distribution architecture. So each home has an optical network uh, terminator. Okay, we call this optical network terminator, which is connected by dedicated optical fiber to a neighborhood splitter. Okay, this is the optical fibers with the splitters. Uh, ONT is the optical network terminator. Okay, so the splitter combines a number of homes. Okay, so into a single shared optical fiber, which connects to an optical line terminator in the telco's central office. The OLT, providing conversion between optical and electrical signals, connects to the internet via a telco router. In locations where the SL cable and FTTH are not available, for example, in some rural settings, a satellite link can be used to connect residents to the internet at speed of more than 1 megabit per second. For example, satellite networks in Malaysia, one of them is what we call as Privasat. Okay, and then so next would be, how does this signals, okay, how does we create the transmission of multiple signals, okay, within one link? So we use a technique of multiplexing. So what is a multiplexing? It's a set of techniques that allow simultaneous transmission of a multiple signals across one link. So within this one link, we divide it into several channels, okay, to provide a parallel transmissions, okay. So there are several applications of multiplexers. One, communication system. Okay, it has a both communication network and a transmission system. So by using a multiplexer, the efficiency of the communication system can be increased by allowing the transmission of data, such as audio and video data from different channels through single lines or cables. Another application is telephone networks. In telephone networks, multiple audio signals are integrated on a single line of transmission with the help of a multiplexer. And one of another example is that transmission from the computer system of a satellite. The multiplexer is used to transmit the data signals from the computer system of a spacecraft or a satellite to the ground system by using a GSM satellite. Okay, so because we have a lot of data signals that we need to send out to the to Earth or ground system, then there's also the application of multiplexers. Two categories. Okay, in multiplexing we have analog and digital. Okay, for analog, okay, we use FDM or WDM, and then some of the combination of this. This is the basic one. And then digital, we use TDM. What is a FDM? FDM is an analog multiplexing technique that combines analog signals. It can be applied when the bandwidth of the link is greater than the combined bandwidth of the signals through to be transmitted. Okay, so the link must be greater when it is need to transmit a combinations of signals. Okay, a combination of signals, so the total bandwidth needed must be lesser than the bandwidth of the link provided. Signals generated by each sending device would modulate different carrier frequencies, so these modulated signals are then combined into a single composite signal that can be transported by the link. Carrier frequencies are separated by sufficient bandwidth to accommodate the modulated signal. So these bandwidth ranges are the channels through which the various signals travel. So the channel can be separated by strips of unused bandwidth, or what we call as guard bands, to prevent signals from overlapping. So in addition, carrier frequencies must not interfere with the original data frequencies. So as you can see in the figure, okay, usually each of this channel, okay, is separated with the guard bands, like a strip of unused bandwidth, so that there is no interference or overlapping signals. Okay, as you can see, the actual application is very similar to the radio application. So when you try to open a certain radio station, they would use a different bandwidth, okay, for you to access. Okay, now this is the process of frequency division multiplexing. So in this case we are using a telephone, okay, source. So each of these source will generate a signal of a similar frequency range, and then okay, because the voices is in between the 4 kilobit per seconds, right? So 4 kilohertz, okay, until 33 kilohertz. So that's why, okay, they would have a similar frequency range. And then when it crosses to the multiplexer, this signal will be modulated into a different frequency carrier. Okay, the resulting modulated signals are then combined into a signal composite signal that is sent over a media link that has enough bandwidth to accommodate it. Now, when it reached to the destinations, okay, it will go to the process of the multiplexing. This is a demultiplexer. It's because of multiplexer can become a demultiplexer. Now, the multiplexer would use a series of filters to decompose the multiplex signal into its constituent component signals, a very signature of its own. Okay, so the individual signals are then sent to the demodulator, and then they would separate, okay, the individual signals, okay, from the carrier, and then passes them to the output. Okay, so assume that a voice channel occupies a bandwidth of 4 kilohertz. We need to combine 3 voice channels into a link with a bandwidth of 12 kilohertz. So the link has a bandwidth of 12 kilohertz. We need to check first if it's enough to transmit a voice channel. Okay, 3 voice channel. So the 3 voice channels need to be combined. Okay, and then with the bandwidth from 20 to 32 kilohertz. So what would be the configuration using the FDM without the use of a guard band? So we know that the voice channels has a bandwidth of 4 kilohertz, but then the link, okay, has a bandwidth size, okay, of 12 kilohertz, ranging from 20 to 32. So the first channels will occupy 20 to 24. And then the second channel will occupy the channel 24 to 28. And then the third channel will occupy the bandwidth from 28 to 32. Okay, so after that, okay, they are modulated together, modulated into specific carrier for each of these range, and then combined together. Okay, they are combined and then pass through to the bandwidth, to the link, and then when it reach to the multiplexer, it will be filtered out. Okay, they will be filtered out and then separate, okay, these individual signals. Okay, separate these individual signals with their each field carrier signals. Okay, after these carrier signals have been separated, what's left is the original voice data. Okay, so let's say we have 5 channels, each with 100 kilohertz bandwidth, and then it needs to be multiplexed together. So what would be the minimum bandwidth of the link if there is a need for a guide band of 10 kilohertz between the channels to prevent interference? So for 5 channels, we need at least 4 guide bands. This means that the required bandwidth is at least one channel require 100 kilohertz, so we times 5, and then plus with 4 guide bands. Okay, so these 4 guide bands consume 10 kilohertz. Okay, so 4 times 10 is equivalent to 40, so add it together with 5 times hundreds. So the total required bandwidth must be at least 540 kilohertz. So this is the example of implementation in a figure that you can see here. So in between these 5 channels, we need 1 guide band, 2 guide band, 3 guide band, 4 guide band, right? Now, analog carrier system. Okay, how does the multiplexing happens in the telephone? So to maximize the efficiency of the infrastructure, the telephone companies have traditionally multiplex signals from lower bandwidth lines, okay, into the higher bandwidth lines. So we start with the lower bandwidth line and then we multiplex it together. Okay, so 12 voice channels are multiplexed onto one higher bandwidth line to create a group. Okay, so a group has 48 kilohertz. Okay, because of one channel has 4 kilohertz bandwidth. So times 12 voice channels, so we have 48 kilohertz. Okay, so and then up to 5 groups can be multiplexed together to create a composite signal, which we call a supergroup. Okay, where this supergroup has a bandwidth of 240 kilohertz. Okay, because we have 5 groups and each group is 12 voice channels, so 5 times 12 is actually 60 voice channels for each of these super group. So we 10 supergroups can be multiplexed to create a master group. Okay, and then 6 master group can be multiplexed together to create a jumbo group. Okay, next, wavelength division multiplexing, okay, or WDM. WDM is an analog multiplexing technique to combine optical signals. Usually it used in fiber optics. So if you are taking subjects of fiber optics, then you would learn so far a little bit more advanced in this part. Now, how does light can be multiplexed and demultiplexed? They use the concept physics of prism. So the each of these signals, okay, have a different scope, okay, different degrees, okay, degrees of light that is passing through the link. Okay, so as you can see, they have a different degree of bending the light. So and then they are combined together. Okay, they are combined together at one end. Okay, and then pass through to the fiber optic cable. And then when it reach to a demultiplexer, okay, so based on a certain angle, it will be separated. okay, to a different signal. So that's the gist of WDM. For a time division multiplexing, TDM is a digital process that allows several connections to share the high bandwidth of a link. Instead of sharing a portion of the bandwidth as in FDM, time is shared. So each connection occupies a portion of time in the link. Okay, so that's why we call it as a digital, because of at the same time, okay, they are sharing the portions. Okay, the time is shared. So means that at one time only one devices can have that resources. So we can divide TDM into two different schemes: synchronous and statistical. So for this course, we will focus on synchronous TDM. Now in synchronous TDM, a round of data units from each input connections is collected into a frame. So we divide it into frames, okay? And then let's say if we have n connections, okay, several connections comes from how many hosts that we have so far, okay? So let's say in this example we have three connections. So a frame is divided into n times slots. Okay, so since we have three resources, we divide it by three, and then after that, and one slot is allocated for each unit. Okay, so one for each input line, like a channel. So if the duration of the input unit is T, okay, so one unit here is T time. So the duration of each slot is T divided by N. Okay, and here is the how many slot that we have, eh? Alright, so the data rate of the link is n times faster and the unit durations is n times shorter to guarantee the flow of data. Okay, as in this example, as you can see, okay, it will be multiplexed together by sending out one frame, okay, one slot, one data unit to the first frame here. So A1 would be slot into the first frame. B1 after that, the B1 would be slotted into frame 1. And then C1 will be slotted into C1. And then it will continue to the next unit, A2. Okay, would be slot into frame 2, B2, and then C2. And then continue. Okay, so that every host, okay, or every unit have a load balancing. Okay, they have fair balance, fair distribution of the resources. Okay, for 1 kilobits per second connections are multiplexed together. So a unit is 1 bit. Okay, means that one unit of the frame here contain 1 bit. Okay, 1 bit of data. So find the duration of 1 bit before multiplexing, and then the transmission rate of the link. Third one is the duration of a time slot and the duration of a frame. So we can answer the questions as the duration of 1 bit is 1 over 1 kilobit per second, because we have four 1 kilobit per second connections. Okay, so 1 kilobit per second is for one channel. So what we have is that the duration for 1 bit would be 1 divided by 1000, which is equivalent to 0.001 seconds or 1 milliseconds. And then the rate of the link, okay, because we multiplex together, so 4 times 1 is equivalent to 4 kilobits per second. And then what is the duration of a time slot? Okay, the duration of a time slot is equivalent to 1 divided by 4, okay, milliseconds, which is equivalent to 250 microseconds. And then what will be the duration of a frame? Okay, so the duration of a frame is equivalent to the duration of 1 bit, which is 1 millisecond. Okay. TDM can be visualized as two fast rotating switches, one on the multiplexing side and then the other on the demultiplexing side, and they can interchange together. So the switches are synchronized and rotate at the same speed, but in the opposite directions. Okay, you will see later on. On the left side is the multiplexing side. As the switch open in front of a connection, so it will start to open for unit A. Okay, and then that connection has the opportunity to send unit A1 onto the path. Okay, so these switches, okay, would pick up the A1 and then slot into the frame. So these, after that, okay, it will go to the next unit, okay, and then slot in that unit, okay. Like, for example, B here doesn't have any unit. So because they don't have any unit, they will go to the next host. Okay, next host we have C1. So C1 will be picked up and then slot into frame 1. Okay, the same process rotate back again. So the switch will rotate to face host A back again. So this time it would slot in, it will pick up A2 to slot in into frame 2, and then B2 to slot into frame 2, and then on host C, they don't have it, right? So they would leave that space, okay, and then continue with the next host. Okay, let's say this frame 1 has been completed, so they will send out to through the link. Okay, in this case, the demultiplexing side, the switch will open in front of the connection here, so it will face the A1 unit. So, and then it will receive A1 and then send it out to the buffer on host A. So, A1 will be sent out to the host A buffer, and then C1 also will be sent to the C host. Okay? And then after that, if it receive frame 2, it will receive A2 and then B2. Okay, there is no unit on C. So they will continue and rotate. So do note the arrow of the rotations is opposite to each other. Okay. Now, 4 channels are multiplexed using TDM. So, if each channel sends 100 bytes per second and we multiplex 1 byte per channel. Okay, so show the frame traveling on the link, the size of the frame in byte or bit, and then the frame rate, frame per second, the duration of a frame in one frame, and the bit rate of the link. So, here, there are 4 channels, and each channel will send 100 bytes per second. And then each frame, okay, so each frame would be multiplexed 1 byte per channel. So we have 4 channels. So each of these frame will contain 1 byte, 1 byte, 1 byte, 1 byte. So when you draw the frames or when you draw the figure, you should be able to get the answer. The frame size would be 4 bytes or 32 bits. And then we can calculate the durations. So the size of the frame is 1 frame is equivalent to 4 channels, and 1 frame contain 1 byte. So 4 channels means that 4 channels time 1 byte is equivalent to 4 bytes. So 4 bytes is also equivalent to 32 bits. Okay, because of 1 byte is equivalent to 8 bits. And then frame rate, because of how many bits per second that we can send out. Okay, so because of the channel can send 100 bytes. Okay, so means that if it's a 4 channels, so it can become 400 bytes per second. Okay, and then we divide it by 4 bytes to get 1 frame durations. So you will get 100 frames per second. And then frame duration, if we have 100 frames, which is equivalent to 1 second, so 1 frame is equivalent to 1 divided by 100 frame, which is times 1 second, which is equivalent to 0.01 second. So what is the bit rate for the link? Okay, bit rate is must be in a bit. So previously we calculate it using a byte, right? 400 byte per second. So convert it into a bit. 400 byte per second. Okay, times 8, you should get 8. 4 times 8 is 32. Okay, so 3,200 bit per second. Okay, and then a multiplexer combines 400 kilobits per second channel using a time slot of 2 bits. So show the output with 4 uninformed inputs. So what is the frame rate? What is the frame duration? What is the bit rate? What is the bit duration? So in this case, we have 400 kilobits per second channels using a time slot of 2 bits. So one slot contains 2 bits. So show the output with 4 uninformed inputs. So we have one frame here contained 8 bits. Okay. So what would be the frame rate? Okay, because we send 100 kilobits per second, and then each of these frame contain 2 bits, okay, from each of the channel. So we would have 50,000, okay, so 50,000 of bits. Okay, so to get the frame duration, so 1 divided by 50,000 per seconds, which is equivalent to 20 millisecond. Okay. Now, look at the calculation. We can answer that size of frame because we have one frame equal to 4 channels, and at each of these channels, okay, or time slot, okay, each of the slot have 2 bits. So 4 times 2 is 8 bits. And then the frame rate, because total bandwidth of the combination of 4 times 100 kilobit per second is 400 kilobit per second. And then when we want to know the frame rate, which is 8 bits, so we divide it by 8. Okay, you will get 50k frame per second. Now, what is the duration for each frame? So for 50k frame is equivalent to 1 second. So 1 divided by 50k frame is also equivalent to 20 times 10 power of negative 3 seconds. So the answer is to 20 milliseconds. And then what would be the bit rate for the link? Okay, because we have the 50k frame per seconds or the frame rate. Okay, so 50k frame per second is times with one frame is equivalent to 8 bit per second. So 50 times 8 is equivalent to 400 kilobits per second. Okay, now this is one of the issue in the synchronous. It's because of synchronous is not as efficient as it could be. If a source does not have a data to send, the corresponding slot in the output frame is empty, such as in this example. Okay, so empty slot means wasted slots. So that's why we also need to have some method. Okay, so usually they propose for this one, okay, because of synchronous here is not efficient. Usually they propose the statistical TDM, okay, using a statistical TDM instead of synchronous. And then, okay, let's say we are using the TDM. Because of the speed in between the holes, okay, one on one end to another end, so the speed itself also would mix up, okay, would give some problem with the framings when they are trying to interpret the frame that they have received. Okay, so which one is from frame 1 and then which one is from frame 2? So that's why because of the differences between the speed of each end, okay, they propose using a synchronization pattern. So for every frame, okay, the first frame will be added with one framing bit. The second frame will be different to show that this one is on the next frame, a new frame. And then for the frame 3, they use one back again to show this is another frame, a new frame. Okay? Right. So we have finished the multiplexing. Now, I would introduce about the transmission media, where why do you justify of using this type of media? All right. Remember, the signals are transmitted in the form of electromagnetic energy. For example, radio wave, infrared light, visible light, UV light, and then cosmic rays. So each constitutes a portion of the electromagnetic spectrum. Okay, remember last time I have mentioned about the physical layer. The physical layer means that the data must be transported or transmitted, okay, using a bit 1 or 0 in this case, and then encoded again, okay, to suit the type of transmission medium. Then it can be sent out or transmitted to the other end. Okay, so there are several types of transmission media: conducted, fiber optic, wireless. So for conducted media, we have twisted pair cable and coaxial cable. I'm sure you remember about the twisted pair cable. Okay, it's because of it's an electromagnetic. It's a conducted. Okay, both of them. Okay, but the differences is that twisted pair cable consists of two conductors coppers that is insulated and twisted together. That's where the names comes from. Okay, one of these pair, okay, in between this pair, one of them is to carry signals to the receiver, like carrying data. And then another one is as a ground reference. So the data rates that can be achieved depend on the thickness of the wire and the distance between the transmitter and receiver. However, they can suffer from the interference and the crosstalk. Okay, when they suffer from the longer distance, so some of them will have some noise on the data. So the number of twists per unit of length, okay, for example in inch, would determine the quality of the cable. So note that more twists means better quality. So there are two types of twisted pair. We have unshielded and shielded. UTP or unshielded twisted pair is the most common use compared to the STP. Okay, why? The STP has an extra metal shield to protect, okay, the inner conductor here. Okay, so that there's lesser interference happens. Okay, that's why it is much more expensive. EIA classifies a twisted pair into 6 categories, which are determined by cable quality and for specific uses. Okay, for each of this category, they have different bandwidth, different data rate. Okay, and then conversion data, which is if it's a digital or analog, and then usage. Okay, on which application it is applied to. Okay, so if you still have the telephone line that is still using the copper cable, then it's cat 1. And then if it's a T1 line, most of the time it's on Europe, so it's a cat 2. But then the rest, okay, cat 3, 4, 5, and 6 is used on LAN. But in a common applications, okay, most of the organizations, okay, would use the cat 6, okay, and then lesser and lesser for the others. Okay, so what are the performance when you are using a twisted pair? Measured by comparing attenuation. Remember, attenuation is the loss of signal strength versus frequency and distance. So note that in case of frequency is larger than 100 kilohertz, this one on this gap, okay, on this scale, okay, you should be able to see that the attenuation would sharply increase. Okay, the gauge is the measure of the thickness of the wire. The higher it is, the larger, the more thicker, the cable it is. Okay, you should be able to see it here. Okay. Um, sorry. The gauge here is that this one, the lesser than that is the more the thickness it is. All right. So coaxial cable coaxial cable signals carry signals of higher frequency ranges than the twisted pair. Okay, their structure is to protect against noise. It is categorized by the radio government ratings, which denotes a unique set of physical specifications. The wire gauge of the inner conductor, thickness and type of inner and the inner insulator, this one inner insulator, the constructions of the field and the size and the type of the outer casing would determine the category of the coaxial cable. Okay, so they have three categories: RG59, 58, and 11. Okay, with impedance or the strength of signals. Okay, but in this case, different usage application. And then compare the performance, okay, by comparing attenuation versus frequency and distance. The distance, the attenuation is much higher in coaxial compared to the twisted pair cable. Okay, as you can see, after it reach 1 kilohertz, okay, the attenuation is much more higher. Reason is that when you have a much higher bandwidth, therefore the signal weaken rapidly and needs the frequent use of repeaters. Next, fiber optic. Okay, so fiber optic use light. So the nature of light is that it's a straight line when travels through a single uniform substance. And then it will change direction when travels through different substance. Okay, for example, in between water and air, okay, so the light will bend, okay, based on the density of the substance. Okay, now if um if the angle of incidence is less than critical angle of refractions, it it will be refracted. Okay, it will be refracted. But then if I is equal to the critical angle, then the light, would bend on a straight line. Okay, like this. Okay, vertically. And then if if the angle of incidence is larger than the critical angle, then reflection will happen. Okay, so based on these principles, that's how they build up the cables. Okay, so it contains a cladding that operate as a level of density, if it's a less density or more density. Okay, so and then this is in between the core. Okay, so in this case they follow this principle. Okay, so that in a certain angle it must be able to reflect back again on the core. So based on this, okay, we look at the propagation mode. So the propagation modes use a multi-mode or single mode. What does it mean multi-mode? Multi-mode refers to multiple beams, okay, like a different signals, multiple signals from a light source move through the core in different path. So under the multi-mode, they have a graded index and step index. Okay, the mode. Okay, for a multi-mode step index, the changes between the constant density of the core and the lower density at the interface results a suddenness changes in the beam motions. Okay, so there's a changes of density between the core and the lower density at the interface, between the interface, so that there's a sudden changes or reflections, okay, in the beam's motion. And then as for multi-mode graded index, the highest density at the core, okay, at the core here, and then it will decrease gradually to its lowest at the edge. Okay, so highest density is in the middle, and then it will be lesser density at the end or at the edge. So what happened is that the reflections shows, okay, a different angle, okay. And then for a single mode, only a highly focused source of light, so that all beams would arrive together with little distortion. Okay, little distortion means that there's not so much angle in this mode. Okay, what is inside the fiber optic? Yes, you must have a glass or plastic core, okay, to reflect the light, and then you must have a cladding to protect the core. After that, protected by the plastic buffer, including the bulletproof vest material Jupon Kevlar, okay, so that the glass or the core will be protected. Okay, different categories have different thickness, what thickness of the core. Okay, so the cladding is the same size, but the core will have a different size. So that's the type of that fiber optic. Okay, and then which mode it can be support. So for in this case 50/125 here is for multi-mode graded index. 62.5 also graded index, and then 100 is also for graded index, and then 7 over 125 used for single mode. Okay, what are the performance? We know that the fiber optic has much more high performance compared to the coaxial and twisted pair. Um, so as you can see on this performance, it has more flatter than compared to the coaxial and twisted pair. And then in this case, they need a less repeater. Okay, so this fiber optic is used on a backbone network such as Sonet. Okay, and also for a hybrid network. And sometimes in a LAN, they use in 100 bits FX and 1000 bits X. Right, wireless. Wireless communication refers to unguided media. So the unguided media means that the signals would broadcast through air and available to anyone who has a device capable of receiving. So you must have a receiver. The spectrum range is from 3 kilohertz to 900 terahertz. So within this wireless here, we have a different category. 3 to 300 gigahertz is radio wave and microwave, and 300 to 400 is infrared, and then 400 to 900 terahertz is light wave. So the type of category is differentiated by radio wave, microwave, and infrared. The radio wave, each of this category is differentiated by the directions, type of sender and receiver, the propagations, and the capability to penetrate the walls. Okay, so in this case, you can see on the radio wave and the microwave have a different type of direction. Okay, and the propagation. Okay, most of the time, radio wave can penetrate wall compared to microwave and also infrared. Okay. So for example, this one it can use omnidirectional antennas. And then it uses sky propagation. So most of the time it used in a multicasting such as one sender, many receiver, like in a FM radio, AM radio, television, maritime radio, and cordless phone or paging. Okay, but for a microwave, it will be used on a one-to-one or unicasting such as cellular phones, satellite networks, and wireless LAN. Okay, as for infrared, it's in everywhere or in front of you, because if you have a Bluetooth, it's part of infrared. The frequency range is very fast, okay, 300 gigahertz to 400 gigahertz with a wavelength of 1 millimeter to 770 nanometers. but it cannot penetrate walls. So that's why your remote control for aircon can be used on any aircon because of they are separated by the walls, right? So yes, it can use for a short range communication. Okay, and also it's used for communication between devices such as keyboards, mouse, PC, and printer. Alright, we have ended for the lecture 3. And then I would stop here for praying, Maghrib praying. For those who are in Malaysian. Okay, so please we will stop and then continue at 7:30. Okay, so 7:30 we will start back again. Okay, all right. Thank you.